Once again, I welcome you all for another lecture on combinational logic circuits. That is a decoder and encoder. In previous classes, we learned about different combinational logic circuits like circuits, subtractor circuits, multiplexer, and demultiplexers. In this class, I'm going to discuss about another type of combinational logic circuits. Those are decoders and encoders. Coming to decoder, a decoder is a combinational logic circuit that converts binary information from encoded inputs to a maximum of 2 power n decoded outputs. That means your decoder have n inputs with a 2 power n outputs. That's the meaning of this n to 2 power n decoder is. Sometimes the number of outputs of decoder is not equal to 2 power n, it is less than 2 power n. Coming to the case here is n to m decoder. That means m value either equal to 2 power n or less than 2 power n. If you consider m is less than 2 power n, the best example is BCD2 7-segment display decoder. We know that BCD is nothing but binary coded decimal. Each and every decimal symbol we are representing with 4 binary bits so that it has a 4 inputs. So n is equal to 4. And it is used to display the decimal digits on 7-segment display. 7-segment display in the sense in our digital watches, the digits are displayed over 7-segment displays. The number of segments present on that display was 7 segments. By using that 7-segment display, we can display the decimal symbols or decimal digits from 0 to 9. That means only 10. So m is equal to 10. So input for this BCD to 7-segment display decoder is 4 bits input. Output is nothing but only 10 outputs. Right? So that here the number of outputs for this BCD to 7-segment decoder is less than 2 power n. Next, coming to the first decoder is 2 to 4 decoder. That means it has a 2 inputs with a 4 outputs. And this is another input enabler. If this enable input is active, then and only based on these input codes. So one of the output was selects. See here, this is the truth table of this. If enable input is 0, what are the combination that should be present on x and y? So that I can written as x, that indicates these are called don't care. Don't care in the sense this value is either 0 or 1. None of your output is active. That means no output value at a D0 to D3 is equal to 1. That means your decoder is not active condition. So next, if you assume that this enable signal is active, that means E is equal to 1. Your decoder is active. Now, based on the combination present on this X and Y inputs, one of these decoder output becomes 1. See here, E is equal to 1. For case XY value is 0, 0. That means we select D0, D0 value equal to 1. It is somewhat similar to the demultiplexer case. The demultiplexer, the selection lines are X and Y, and input is Dn. If X and Y is 0, 0, the D inverse reaches to output Y naught. But here it is a decoder circuit. Always output here is 1 based on the code that was present at input side of your decoder. The next combination is XY value is 0, 1. That means we select a D1. That means D1 value is 1. And next case is 1, 0. Then we select D2. That means D2 value equal to 1. And remaining outputs are 0. If both are 1, 1, then we select D3. and remaining 3 outputs are 0. Now, if you go and realize this decoder, so D naught output can be produced by an AND gate. For the cases, enable signal is 1 as well as x value 0, y value 0. In the sense, we written as a product term is E x bar, y bar. See here, friends. X, y bar. This is x. So output of NOT gate becomes x bar. This is a y input. NOT gate output becomes y bar. These two are given to the input of AND gate. Defaultly, one more input to all these AND gates that should be implicitly exist, which is an enable input. So that D naught is equal to x bar, y bar. Similarly, D1 is equal to 1 for x bar y. D2 is equal to 1 for x, y bar. And D3 is equal to 1 for x, y. So the decoder completely contains internally an AND gates. AND gate outputs are nothing but the output of decoder. Next, we go to higher order decoder, that is 3 to 8 decoder. That means it has a 3 inputs, let it be A0, A1, A2, are decoded into 8 outputs, that is Y0 through Y7. Each output yi represents one of the min terms of 3 input variables because the decoder internally contains AND gates. AND gate output is nothing but a product term. Basically, a product term, most of the cases we consider as min term. And yi is equal to 1 when the binary number present on A2, A1, A0 is equal to I. That means yi, instead of yi, if I write y1, that means A2, A1, A0 is 0, 0, 1. So that's the meaning of this. In shortcut, yi is equal to mi because mi is nothing but min term notation. Always we know that min term value is equal to 1. The output variables are mutually exclusively. Exactly one output has a value 1 at any time and other 7 outputs for this case is equal to 0. That means mutually exclusive. Mutual understand. That means only one output of your decoder is active and rest of the outputs are inactive. So coming to its block diagram representation, this is my decoder with inputs XYZ, 3 input and 8 outputs D0 to D7 with an enable input is E. This enable input is default because it is an active then and only based on the code that present on XYZ, which selects one of the output. If enable signal is not active, then the decoder is not active, then whatever the combination present on this, all your outputs are equal to 0. So here my assumption is this decoder enable signal is active. So that here I consider the combination present on XYZ. Based on the combination present on XYZ, I select one of my output. So 3 variables, 8 different combinations, that is from 000 to 777. Each combination, let it be one code. That code selects one of the output of your decoder. If my XYZ is equal to 0, 0, I select D0. So D0 becomes 1. The rest of the outputs are 0. Next combination present on XYZ is 0, 0, 1. That means I select D1. So D1 is 1. The rest of the outputs are 0. In a similar way, based on the combination present on XYZ, we select the outputs of a decoder. Only one output at a time can be selected. That output becomes 1. The rest of the outputs are is equal to 0. If you go and write the selected output value is 1, that means that is correspond to the min term. So that D0 is equivalent to X bar, Y bar, Z bar, that is M0. D1 is equivalent to X bar, Y bar, Z, that is M1. And similarly, D7 is equal to XYZ, that means M7. This is the internal logic diagram of your 3 to 8 decoder. I have 8 AND gates. Each AND gate have 3 inputs. Originally, fourth input also exists. That is an enable input. I'm not mentioned here is. But you remember, if that enable signal is active, then and only this decoder will work. Next, 3 to 8 decoder by using 2 to 4 decoder. That means making a higher order decoder by using lower order decoders. So my decoder have an 8 outputs, so that I'll go and take 2 to 4 decoder, because each decoder have 4 outputs. So I need same type of decoders too. That is, each one have 4 output. So 2 fours are 8 outputs. So see here, friends, this is one 2 to 4 decoder, and this is another 2 to 4 decoder. If you observe this truth table, list two significant variables, y, z. It is changing from 0, 0 to 1, 1 for first 4 combinations. The same thing is repeat for the remaining 4 combinations. So that for the first stage 2 to 4 decoders, the selection of your outputs I do with the help of y and z variables. See here. So y and z are combinedly applied to both the decoders. So then the another variable x is used as an enable signal for this decoder. See here, friends, this is the first decoder which is responsible for the outputs D0 to D3. And this is the second decoder which is responsible for the remaining 4 outputs, that is D4 to D7. For D0 to D3, x value is equal to 0. See here, friends, x is equal to 0. It is passes through a NOT gate, it becomes 1. This decoder is active because here we have an enable input E. Same x is applied to this decoder at an enable input. Because of 0, this decoder is not active. Next case, if x is equal to 1, then the output of this inverter becomes 0, then this decoder is off. The same one is applied to enable signal of second decoder, then your second decoder is active, and which is responsible for the outputs D4 to D7. See here. So first decoder is responsible for D0 to D3, and the second decoder is responsible for D4 to D7. So like this, we can implement higher order decoders by using lower order decoders. Similarly, 4 to 16 decoder. See here, friends. That means it has a 4 inputs, W, X, Y, Z, and 16 outputs. For this, default input was enable input. If that enable input is active, then and only based on the combination present on this inputs, we select one of these outputs, D0 to D15. See here. So W, X, Y, Z, 0, 0, D0 was selects, 0001, D1 selects, 0010, D2 selects, 0011, D3 selects. Like that, 4 ones that will select D15. That is the last output of your decoder. The same 4 to 16 decoder implementation by using 3 to 8 decoder, because here I have a decoder have 8 outputs, but a required decoder have a 16 outputs, so that I need 3 to 8 decoders. These are 3 to 8 decoders. The topmost one is responsible for the outputs D0 to D7, and the bottom decoder is responsible for D8 to D15. If you observe the previous truth table, W, X, Y, Z, out of 4 variables, W is consistently 0 for first 8 combinations, that is for D0 to D7 selection, and W is 1 for the remaining 8 output signals selection, that is D8 to D15. So that this W signal is act as enable signal to these 2 decoders. And the selection of the outputs of these decoders we do with the help of least significant 3 more variables, that is X, Y, Z. So that X, Y, Z are directly connected to the decoder inputs for selection of the outputs, and W is used for the selection of enable input. So that means that is used to select either upper decoder or bottom decoder. See here, that is the truth table. So see here, friends, W value is 0 for D0 to D7. So that is responsible for upper decoder. If it is 0 here, 0 is applied here, the bottom decoder is off, but output of this NOT gate becomes 1. That is given to the enable input of upper decoder, so that upper decoder is active. Then based on the combination present on XYZ, we select one of the output of decoder D0 to D7. When W is equal to 1, that is happened for D8 output to D15 output. So that if W is equal to 1, the bottom decoder is active. At the same time, it is 1, the output of NOT gate becomes 0. Then upper decoder is inactive. For this case, lower decoder is active for selection of an outputs D8 to D15. The same 4 to 16 decoder we can implement by using 2 to 4 decoders. Actually, we are not using 4, we are using 5. Because at the output side, we are using 2 to 4 decoders because the required decoder have a 16 outputs, but your source decoder have only 4 outputs. 4 into 4, that is 16 outputs. See here, friends, these are the 2 to 4 decoders. The first decoder is responsible for an output D0 to D3. The second one is responsible for another 4 outputs D4 to D7. Third one is responsible for next 4, that is D8 to D11. And next, last one is responsible for another 4 outputs, that is D12 to D15. And the selection of these inputs is out and out we do with the help of least 2 significant variables, that is C and D. And we left with 2 more variables. Those are given to the inputs for the most significant side decoder 2 to 4 decoder, which generates enable signal for the lower stage decoders. AB value is consistently 0 for the outputs D0 to D3. So whenever I have A and B value both are 0, 0, D0 was selects. It is act as enable signal for decoder or decoder 1, which is responsible for selection of D0 to D3 outputs. If AB value was 0, 1, then one output was selects, which is act as an enable signal for second 2 to 4 decoder, which is responsible for D4 to D7. And next it is 1, 0. The second output was selects, which is act as enable signal for our third 2 to 4 decoder, which is responsible for an outputs D8 to D11. And last AB value is 1, 1, which selects the last output here, that is the third output, which is act as enable signal for last decoder, which is responsible for D12 to D15. See here. So CD continuously changing from 0, 0 to 1, 1 for every 4 combinations. So D1 to D3, that is for first. Next, D4 to D7, that is next. Next, D8 to D11. Next, D12 to D15. So like this, we are making higher order decoders with the help of lower order decoders. Next one is implementation of some combinational logic circuit. Here is full adder by using decoder. I know that the functionality of full adder is which can perform addition between 3 binary bits at a time. If I go and take the inputs of my full adder is XYZ, the outputs are sum and carry. Then sum expression is sum is 1 for 1, 2, 4, 7. This I directly written here. And carry is 1 for 3, 5, 6, 7. So here I select a decoder such that the number of variables present in the Boolean function is equivalent to the number of inputs of your decoder. So the variables here is act as the inputs of your decoder is. So X, Y, Z. So Z have 2 power 0, that is the least significant. Y is at 2 power 1 input, that is next higher order. X is at 2 square, that is higher order. So for 3 to 8 decoder, these are 8 outputs. For implementation of Boolean functions by using a decoder, we need a decoder along with some logic gates. So here I took my Boolean functions are in standard sum of products. Internal to decoder, I have an AND gates. So AND gate outputs are given to an OR gate to design sum of products function. To produce a sum output, I took one OR gate. For this OR gate, have a 4 inputs, that is one output, one input, 2, 4, 7, that is an output of your decoder, one output, 2 output, 4 output, and then 7 output. For these 7 cases, your sum value is equal to 1. I know that whatever the decoder we selects with the help of inputs, that corresponding output value becomes 1. So based on that, here these terms related outputs of decoder are connected to the input of R8. In a similar way, carry case also. Carry can be produced by another OR gate which have a 4 inputs, that is a 3, 5, 6 and then 7. Like this, I'm going to design. For example, if x equal to 1, y equal to 1, z equal to 0, 1, 1, 0, your sum is equal to 1 and then sum equal to 0 and carry equal to 1. So how it will present? See here. So for this combination, that is 6 was active, right? So 1, 1, 0, 6 was active. So carry value is 1. So 6 is given to OR gate which can be produced by carry. And the 6 was not connected to sum, so that sum output is equal to 0. So like this, we can implement the Boolean functions 0 and 1. And next, another one is encoder circuits. These are the reverse function which was performed by decoders. See here, this is your encoder circuit which may have 2 power n inputs and n outputs. That means one of your inputs of encoder is active. Its coded output was present at the output of your encoder circuit is. So definition of encoder is, an encoder is a combinational logic circuit that converts the binary information in the form of a 2 power n input lines into n output lines, which represents n-bit code was produced for an input. So what are the input? Here we select that corresponding code should be presented output of your encoder is. Only one input is active at any instant of time. The selected input or activated input, binary code was present at output or binary pattern was present at output. The examples of encoders are 4 to 2 encoder or 8 to 3 encoder or 16 to 4 encoder. Like that, we have different encoders. Let it be here I consider 4 to 2 encoder. That means my encoder has a 4 inputs and 2 outputs. As usually, we have an enable input. If this enable input is active, then one of the input of encoder is active. Its corresponding binary code was produced at the output of encoder. If enable signal is not active, even though one of the input of encoder becomes 1, the output of your encoder may not be defined. It is don't care. See here, friends, that should be the truth here. So my inputs are 4 inputs, A0, A1, A2, A3, along with enable input. If enable input is not active, what are the combination that should be present on A0, A1, A2, A3? That means between 1 or 0. Your outputs are simply 0. That means the outputs are not active. If enable input is active, then we'll go on to consider the combination present on A0 to A3. If enable signal is 1, A0 is 1, remaining all are 0. That means your encoder has to produce binary code for the input A0. So A0 is 1, remaining all are 0. So for 0, XY value is 0, 0. Next combination enable input is 1. If I select A1, that is A1 is 1, remaining all are zeros, then A1 binary code was produced at the output of XY, that is 0, 1. If A2 was selected when enable signal is active, A2 equivalent binary code was present at output of encoder, that is at XY, that is 1, 0. Similarly for A3, the code produced by encoder is 1. So I'll go and write the output expressions for them. So X is 1 for only 2 cases, that is A2 plus and then A3. A2 plus A3. Then Y is 1 for A1 and 1 for A3. So Y is equal to A1, A3. See here, this is the logic diagram. So Y is equal to A1, A3 and X is equal to A2, A3. And A0 we have, these are the inputs and these are the outputs. Similarly, 8 to 3 encoder. That means 8 inputs, 3 outputs with enable input. So see here the same conditions. That is, if enable input is not active, what are the combination present on this A0 to A7? Your encoder can't respond. That means the output of encoder is 0, 0, 0. So next, if enable input is active, then we select one of these inputs. That means one of your encoder is active. That activated input binary code was produced at the output of this encoder, like previous case. So A0 is active here. So the corresponding code produced at output of encoder is 0, 0, 0. For A4 is active, then the code produced on XYZ is 1, 0, 0. And A7 is active, then the code produced at the output of encoder is 1, 1, 1. So the major drawback of this encoder is at any instant of time, only one input should be active. The rest of the input should be inactive. But coming to reality, it may not be happens. If you go for different circuits, there is a possibility for more than one input of encoder should be active. That time, this encoder can't produce valid code at an output. To overcome this difficulty, we shifted to another variety of encoders. Those are called priority encoder. So what is the specialty of this? We'll go and check it. This is my 422 priority encoder. So here the inputs are 4 inputs, 2 outputs along with an enable input. Same case, but this is general encoder circuit case. But see here the input conditions. Your encoder will produce code for A0 only when the remaining 3 inputs are 0. That means A0 have a lowest priority than A3. A3 have a highest priority. Next highest priority goes to A2. Next highest priority goes to A1. Least priority goes to A0. This priority encoder produces a code for A0, which have a lowest priority only when the higher priority inputs A1 to A3 are not active. See here, that was happened here. A1, A2, A3 all are 0. Then and only this encoder will produce valid code at output 0, 0. Next, for A1 generation, A2, A3 should be inactive because these have a higher priority than this. So A1 is 1, A2, A3 should be 0. The time A0 value may be 1 or 0. It means it may active or an inactive. But this encoder can produce a code for only A1 because the priority of A1 is higher than A0. So that A0 value we consider as don't care. Next, this encoder can produce a code for A2 only when A3 was 0, A3 0. That time, whatever the value present on A1, A0, your encoder can produce code for only A2 because A2 priority is more than A1 and A0. See here, A2 is 1, A3 is 0, and A0, A1 is don't care. Previously, it is a 0, 0 for normal encoder, but it is a priority encoder so that these values are don't cares. And last, for generation of A3 code by this priority encoder, what are the combination that may present on A2, A1, A0? It should produce a binary code for only A3. The reason is it have a highest priority compared to remaining inputs. That was proved here. A3 value is 1. A2, A1, A0 values are don't care. Still your priority encoder produce code for A3, which is equal to 1, 1. So this is useful for us compared to normal encoder cell. Similarly, this is 8 to 3 priority encoder. So here lowest priority goes to A0, highest priority goes to A7. If enable signal is not active, what are the combination present on A0 to A7? The XYZ values are 0. If enable signal is active, then based on these inputs, XYZ can produce an output. So A0 can get a code at output of this priority encoder only when A1 to A7 are zeros. See here, all are zeros. Only A0, that is D0 is. So for that code is 000. Next for A1, it can produce a code 1. Basically here I write it as D1. So only when this A2 to D7 should be active. That means D2 to D7 should be 0. So A not value, that means D not value, whatever it may be, because the priority of this one is lower than A1, means D1. Your priority encoder will produce code for only A1, that is D1 case. So like that, A7 have a highest priority. Your priority encoder produce code for A7. That means D7 is 1. What are the values of A0 to A6 is? If they may active or inactive, so that those values are don't care. Your priority encoder will only produce code for A7. So this is priority encoder. Thank you for patient listening. So we will meet on next class. Thank you.